Welcome back to the Deep Dive. You know, for decades, when we talked about protecting patient data, the whole conversation was pretty straightforward.
Right.
We were focused on securing, well, the file folder. You remove the patient names, the social security numbers, all the things we now call PII, personally identifiable information.
And that was the whole game.
That was it. That was the frontier.
And look, that focus made sense for a long time. The biggest risk was just a simple breach of those external identifiers. But what our sources are showing now is that the threat has just fundamentally changed.
How so?
The real tension now is how these massive deep learning models can exploit these intrinsic, almost invisible patterns that are embedded at the pixel level of a CT scan or an MRI.
So we've basically secured the wrapper, but now the computer can look inside the box.
Precisely.
Okay, so our mission today is to unpack exactly how identifiable information leaks from these medical images. And we're talking way beyond just patient names. We're looking at facial structures, digital vendor signatures, even outright biometric fingerprints.
And crucially, we'll get into the cutting-edge privacy techniques being designed to fight back and the new and pretty unexpected vulnerabilities that those solutions are introducing themselves.
When you look at the big picture, the core tension is really clear. AI needs these gargantuan, high-quality data sets to even function.
It's totally dependent on them.
But that dependence just fundamentally clashes with regulatory frameworks like HIPAA here in the US or GDPR in Europe, which are designed to protect the individual.
Exactly.
So before we dig into the details, let's nail down some core vocabulary, because I hear these terms used interchangeably all the time, and they really shouldn't be.
Oh, absolutely.
We have three big concepts: de-identification, anonymization, and pseudonymization.
Right. Let's start with de-identification. This is what IPA in the US primarily relies on. And it's really a process of selective removal and careful handling of information. You're sort of checking off a list of items to prevent direct re-identification.
Okay, so it's about being careful, following a process.
Okay.
Then you have anonymization.
Anonymization is the next level. It's the complete, irreversible removal of PII. The goal is to make re-identification practically impossible.
Which sounds great. That sounds like the ultimate goal for privacy.
It does, but our sources highlight a major problem. It often strips away so much essential clinical data that researchers need it, which, makes it pretty much unsuitable for research. You get perfect privacy, but functionally useless data.
And that brings us to the third one, pseudonymization. This is the one Europe often mandates for research under regulations like GDPR.
Yes. And the way it works is, well, think of it like a library card.
Okay.
Instead of putting your name on a checkout slip, the library assigns a unique coded label to that record. The researchers only ever see the code, not your name. The original hospital holds the key, linking the code back to you, but the researchers never see it.
So you can still link data across different studies without ever exposing the original sensitive information.
It's that balance between utility and protection.
That distinction is so crucial. Privacy is a spectrum, and we're always trying to slide that dial towards safety without just killing the utility of the data.
Exactly.
Let's start with segment one then. The old focus, metadata, and what you call the DICOM dilemma.
So metadata is all the non-image information that comes with a medical image. It's the contextual, the technical, the clinical details. Usually it's all embedded right in the DICOM header.
And that includes everything from patient demographics to the really technical scanner settings.
Right. And this breaks down into two types: structured and unstructured.
What's the difference?
Structured data is in predefined formats, numerical values, specific text fields like patient age or the slice thickness. Unstructured is the free text you find in clinical notes or radiology report.
And that free text is where the risk is.
It's inherently riskier, yeah. It requires extra processing, usually with natural language processing, to properly detect and scrub any PII.
What's so interesting to me is the trade-off here. You'd think the safest thing to do is just delete all the metadata. But that's not practical for AI, is it? Why do researchers need to keep it?
They need it for calibration. I mean, for a good AI model, you need structured attributes like the scanning acquisition parameters, the protocols, the characteristics of the scanner vendor. If you strip all that away, you basically introduce noise and bias into your model.
So the AI performs worse in a real hospital?
Then much worse. It adds a ton of complexity without actually improving privacy all that much.
So the early strategies of just converting images to formats like NIFTI to get rid of metadata, that had a real downside.
A huge downside. Modern approaches are much more nuanced. They use updated DICOM standards and special tools to selectively remove the obvious PII, and then they replace other sensitive fields with those safe, pseudonymized codes we talked about.
But based on the sources, there's a big catch, even with these modern tools.
There is.
The performance of the free de-identification toolkits varies wildly. You can't just trust the tool.
You absolutely can't. And that variance just underscores the need for a final verification step. Whether you do it manually or with an automated audit, you have to ensure no residual PII, even in some tiny obscure field, is left behind.
You have to audit the tool.
You have to audit the tool.
All right, let's leave the digital folder behind now and look inside the image itself. This is where the risk becomes truly insidious. We're moving into segment 2. The threats embedded in the pixels themselves.
And what we're finding is that deep learning models can exploit patterns that are utterly invisible to the human eye.
These pixel-level threats, you break them down into 2 categories, right? Direct and indirect.
Yes. Let's start with the direct ones. And the first one is facial features.
The idea that an anonymous MRI scan of your head could still be used to identify you? I mean, it sounds like science fiction.
It's very real. Advances in 3D reconstruction mean these detailed scans inadvertently capture high-fidelity facial features. One study in particular, Stieg et al., showed how shockingly easy this is.
What did they do?
They showed that freely available, just off-the-shelf facial recognition software could successfully re-identify people using 3D renderings from simple MRI head scans.
Wow. So this isn't some complex nation-state attack.
No, not at all. This is a realized risk using common tools you can just go and download.
That is genuinely alarming. So what's the countermeasure? You have to protect the face, but keep the brain anatomy for the diagnosis.
Well, the evolution of the protection is pretty interesting. The early methods were destructive, like something called skull stripping.
Sounds aggressive.
It is. It just completely removes the facial structure. The problem is you sometimes remove anatomy, like the orbits or sinus cavities, that are essential for certain kinds of neuroimaging research.
So you do something more surgical.
Right. So we move to more balanced defacing algorithms, things that selectively obscure features using, say, blurring, which is used in the big Human Connectome Project dataset, or other geometric approaches. But the newest tech is actually using deep learning itself to solve the problem. Specifically, generative models like GANs and autoencoders for a process called refacing.
Refacing, what does that do?
Instead of just removing the face, the AI completely transforms its characteristics. It essentially gives the patient a new digital face.
Oh, that's clever.
It preserves the research value of the underlying anatomy while completely breaking the link to the real person.
Let's move to the second direct pixel threat. Burned-in text. This is the patient name, the hospital logo, the exam details that are visibly overlaid right on the image.
Right. You see it a lot in ultrasound or CT dosimetry. Historically, if the image was noisy, this text was pretty hard to extract reliably.
But not anymore, I'm guessing.
Not anymore. Modern deep learning models and LLMs are now incredibly good optical character recognition. They can detect, isolate, and read this burned-in text with very high accuracy.
But I imagine integrating a powerful LLM into a sensitive clinical pipeline, just to scrub text, that must introduce its own compliance headaches.
It absolutely does. You're now having to use these vast, powerful models on highly sensitive PII, which creates its own set of IPA and organizational challenges. The solution adds a new layer of complexity.
Okay, let's shift to the indirect identifiers, what you call the biometric fingerprint. This is where the AI extracts patterns the human eye would just never see.
And there are 3 main ways this happens. First, demographic information. Deep learning models are surprisingly good at recognizing complex patterns related to a patient's race, age, and sex from the pixel information alone.
Wait, you're telling me that even if I remove every demographic tag from the file,
Yes.
the AI can still look at an X-ray and figure out the patient's race?
That is exactly what the Gikoya et al. Study showed. They found high performance in race prediction across different body parts and different modalities.
That's incredible.
And while that capability is useful for researchers trying to mitigate bias in their models, it's also a serious privacy risk. When you combine this inferred data with other external data sources, the likelihood of re-identification goes way up.
So the mitigation there must be to aggregate the data.
Precisely. You limit the exposure. Demographic reporting should be limited to summary data age by decade, for example, not a specific age like 42. It just raises the bar for an attacker.
What about the equipment itself? If I get an MRI at Hospital A, Does that image have a signature from that specific scanner?
It absolutely does, especially MR images. They retain the strongest imprint because of manufacturing characteristics and, well, fundamental MR physics. CNNs can get very high performance in classifying both vendor Siemens, GE, and so on, and the specific scanning sequence used.
But why is that a major privacy risk for the patient?
In a huge data set, it might not be. But think about a small, specific data set, maybe one for a rare disease or a certain type of surgical implant that was only performed on one specific machine at one hospital.
Ah.
Identifying the vendor in sequence acts as another indirect identifier. It helps an attacker filter down the possibilities very quickly.
And finally, the human body itself is a fingerprint.
Yes. Anatomic features, like your specific skeletal morphology from a chest scan, can function as a unique biometric fingerprint. The Packhäuser study used a twin neural network, a lot like facial recognition systems, and it could determine with very high accuracy if two separate chest X-rays belong to the same person.
And this is the mechanism that allows a linkage attack.
That's right. Even if a patient is totally anonymous in two different public data sets, if an adversary can consistently determine that patient X in dataset A is the same person as patient X in dataset B.
They can start combining information from both sources to build a profile.
Correct. Which means we have to look past simple de-identification.
Okay, so if these traditional methods are failing, we have to look at segment 3, the contemporary technical solutions and the new vulnerabilities they're creating. Let's start with federated learning.
Federated learning, or FL, is a fantastic concept because it solves that core clash between data utility and centralized storage.
How does it work?
Multiple hospitals can collaboratively train a shared AI model without ever exchanging raw data. The core principle is bringing the algorithm to the data. It aligns perfectly with regulations like the European AI Act.
So the raw images stay locked down locally, and only the training gradients get sent to a central server to be aggregated. That sounds like a perfect fix.
It sounds like it.
That's the catch.
The flaw is what's called gradient leakage.
Leakage.
Those gradients that are shared, they're not just abstract numbers. They inherently embed sensitive information about the original training data they were learned from. Adversaries can use an inference attack called gradient disaggregation to work backward.
You're kidding, so they can reconstruct the original image from the update.
They can. The Geiping et al. Study demonstrated exactly that. Input images can be reconstructed directly from those shared gradient updates. The very thing we thought was safe to share is the vulnerability.
It's like sharing a recipe update that accidentally leaks the secret ingredient.
That's a perfect analogy. So we need protections for the gradients themselves. And the two main defenses are differential privacy and homomorphic encryption.
Okay, explain differential privacy simply.
Differential privacy adds carefully calibrated noise to the training gradients before they're shared. The idea is that the noise is just enough to make it impossible to figure out any single patient's contribution. You add noise until the individual is lost in the crowd.
So reconstruction becomes unreliable. Yeah. What about homomorphic encryption? That sounds very technical.
It is, and it's computationally expensive, but the concept is really powerful. The gradients are encrypted, but the central server can still perform math on them, like aggregation, while they remain encrypted.
So the server never sees the raw gradient information.
Never. Which completely shuts down that disaggregation attack.
Let's pivot to the other big solution. Generative models and synthetic data. These are models like GANs and diffusion models that create new, realistic synthetic images.
Right, they're used to augment small or biased data sets. This is essential for meeting compliance standards, especially where regulations say you can only process sensitive data if bias correction can't be achieved any other way.
But the models themselves, even though they create safe data, they introduce a whole new class of vulnerabilities.
Yes, vulnerabilities aimed directly at the model's architecture. The first is called a membership inference attack.
What does that infer?
It tries to determine if a specific patient's data was used in the training set. Generative models can sometimes memorize specific training examples, especially from smaller data sets. An adversary can effectively ask the AI, "Have you seen this person before?" And the model leaks the answer.
And they can do that even without access to the model itself.
Even with just API access in what's called a black box attack. It's a massive issue if we're trying to prove our systems are safe.
And there's a more severe attack.
Yes, the model inversion attack. This is where the adversary tries to reconstruct the model's training data entirely.
And how successful are these attacks in the real world?
Highly successful, at least in research environments. The Lie et al. Study, for example, used a diffusion-based attack that successfully reconstructed training chest x-rays, retaining patient-related features.
So they essentially disclose the original medical images.
Yes. These architectures, designed to augment data, carry this fundamental risk of betraying the source data.
And what's alarming here is the systemic gap in evaluation. Our sources say fewer than half of the studies on synthetic data even formally evaluate privacy.
It's the weakest link. They often rely on surface-level similarity metrics instead of testing against these active attack frameworks. We cannot rely on perceived fidelity. We have to test against membership and model inversion attacks to be sure.
So after all this, what does it all mean? Our deep dive has shown this crucial evolution in privacy. We've moved so far past just stripping PII from metadata.
The challenge now is recognizing this complex, invisible information embedded in the pixels and understanding how these new AI models can exploit it for re-identification.
The urgency feels palpable because these emerging threats, the gradient leakage, the model inversion, they're just not well understood outside of very specialized technical groups.
Not at all. And they require complete rethinking of how we manage data across the entire AI lifecycle.
So the call to action for the industry seems pretty clear. We need standardized, rigorous, interdisciplinary research. We have to bridge the gap between the technical development, the clinical relevance, and the regulatory oversight to make sure these technologies are actually safe in the real world.
And that leads to a final provocative thought for you to consider. The scientific community has to balance the need to mitigate every single one of these rare privacy risks we've discussed.
The vendor signatures, the anatomical fingerprints.
All of it. We have to balance that against the need to prevent an excessive focus on those scenarios. Because if you focus too heavily on every theoretical threat, you could introduce so much complexity that you just compromise the practical clinical utility of the AI. You could slow down medical progress.
So what is the optimal balance between achieving nearly perfect theoretical privacy and ensuring the AI is actually usable and beneficial in a fast-paced hospital?
That's the question we leave you with.
Thank you for diving deep with us today. We'll see you next time.